Oh man, I want to.
Recording, rolling. It's Monday, February 2nd. So I have a demo top class for you guys, give you guys equation review. You guys know we're in the middle of harmonic motion. Right, you guys have an FRQ on your desk, so we'll take a lot of class to look at that. All right, and then, guys, what are you guys gonna have done before Wednesday? AP class here. Yeah, I checked it this morning, and a few guys have done this already. So, no, all right. And I'm looking at in-class quiz on Monday. What we're going to be doing. All right, so all right, let's do a auditory demo here. All right. Were you guys hearing how many beats per second were you guys just hearing?
We're supposed to be counting.
Number, well, pretty close to. Right. Like compared to the second hand on the clock.
Was it one?
Number of beats per second. Yeah, you guys heard one? Okay. Now, if that's true, what we say is the time period between beats.
One.
Yeah. Would you say 1 second? Right. Okay, so guys, if I write the number one, okay, this would be seconds, wouldn't it? So maybe I should put a unit here for seconds. Okay. But if that's true, number of beats per second. Well, maybe that could sort of have a unit too. What do you think the unit is on this? Hertz. Yeah, hertz. HZ could stand for hertz, couldn't it? Okay. So, now if those are units, hertz, seconds, hey, maybe I could come up with a variable character. Like time period could be what letter are we using for time period? Capital T. Okay. And the unit hertz quantifies what variable? Frequency. Yeah. Okay. All right. So here, we got a table started. Let's take a look here. Frequency, time period we got going on. Okay. Let's go ahead a little bit here. About how many beats per second were you guys hearing? 2. So you could call that a frequency of 2 hertz. You guys get that? 2 hertz. Okay. But what's the time period between beats? Half of a second between beats, isn't it? Half a second.
Figure it out.
Like that. You're saying 4? Okay. You guys are hearing 4 beats per second? Okay. Which means how much time between beats? Yeah, 0.25. Yeah, you could call it 0.25 seconds between beats.
Oh.
Well, you gotta see the pattern, right? I keep doubling. So, yeah, let's call that it. Yeah, it said 10, 8, or 8. Okay. Right, so how much time between eggs of a second? Right. Okay. All right. Now we got a few points here. Can you guys come up with a general relationship between frequency and time period? You can say F is what? 1 over T. Okay. Or you can say T is 1 over F. Okay. Okay, so frequency and time period are reciprocals. Okay, you guys remember that? Okay. How about this? Guys, what if I kept ramping up the number of beats per second? Let's say that the frequency in hertz. Okay. Until I get to, what if there was a frequency of 440 hertz? I'm just making something up here. Right, 440 hertz. Okay. Would your brain even be able to distinguish the beats at that point? Or would it sound like a hum? Like a hum. Yeah. Right. Oh, wait a minute. Sounds like a hum. That might correspond to a musical note. Guess what musical note is that right there? Yeah, it's an A note. A note. Right. Okay, so yeah, if you pick up any modern musical instrument, right, and you strike in, well, one of the A notes is 440 hertz. Okay. But you could go down an octave or up an octave, couldn't you? Okay. Does anybody know if you go down 1 octave, what's the frequency down 1 octave? It's still an A note, it's just an A down 1 octave. 220 hertz. Right. And what if you go up an octave?
Or you get 880.
880 hertz. Yeah. Turns out every time you double the frequency, it's the same note, just offset by 1 octave. Yeah. Yeah. Let's do some reviews here. Alright, so you guys did this lab at the beginning of last week. You guys found what's the relationship between time period and all these other variables. Okay? It turns out that the length of the pendulum matters. Okay? There's this relationship here. Okay? Guys, what if I had twice the length of a pendulum? If I double the length of the pendulum, what happens to the time period?
No, it would be
Square root of 2, which is about 1.4 something, right? Yes, square root of 2, about 1.414. Okay, okay. So, okay, so gravity field matters. Okay. But guys, what if I double the mass of the bob? What happens to the time period? Nothing, stays the same. Okay. What if I double this angle from 5 degrees to 10 degrees? What happens to the time period? Yeah, it's still the same. Yeah, here's the block on the spring. Really similar looking formula. So the time period bounce up and down. Right, this is a lab you guys did also. What if I double the gravity field? What happens to the time period? Double the gravity field.
no.
Nothing. Yeah, it's the same time period. Okay. What if I double the mass of the block? Does it take more time or less time to oscillate? Double the mass of the block. Takes more time. It slows it down. How much more time?
Twice.
Not double.
No, just
If you double the mass, 1.4. 1.414. Yeah, you guys think square root of 2. Right. Okay. What if I make this spring really stiff? Really stiff spring. What happens to the time period? Increase or decrease? Decrease. Yeah. Right. If it's a really loose spring, that day, or if it's a really stiff spring, thing like that. Takes no time.
Faster when
Oh, here's the table we just put together, isn't it? Isn't it? This table we just pieced together. You guys came up with this, right? There's a special kind of frequency called angular frequency. All you do is you take the regular frequency, just multiply by 2 pi, right? And okay, so here's some common oscillating scenarios, okay? And that could help you construct this type of equation to make this kind of graph. Right, this is one of the graphs you guys did in your lab last week. Just from that. Right. And those questions that I just went through are the equations that show up on your AP equations. They're right here. Right, so it's just the small set right here. Okay, so you guys know this? Where to find them? How to apply them? Okay. Since I did a kind of a musical example with you guys, I find here. Gotta find some posters related to music here a little bit. Okay. So a lab that I do want to do with you guys later this week is going to be this one, where I have you guys strike a tuning fork over a PVC pipe. This is going to be a PVC pipe in a vat of water. Right? So you have this big old beaker of water. Right? And you can raise and lower the PVC pipe. Okay? There's certain places where the sound will resonate. So you have bing, and you hold it next to the pipe. Okay? And as you raise and lower the pipe, sometimes like yeah, yeah. And then this one did. Yeah. Rear left, right? Okay. And because there's certain standing waves that can be set up. Okay. Now, sound is a longitudinal wave, so it's like all these dots of these high pressure points. Guys, could these be high pressure points? These could be low pressure points. You guys think? Okay. There's certain places where it'll resonate. Okay. Now, what about resonating sound? There's a pretty close to lab table you guys are gonna get. Okay. So if the pipe is open at both ends, right? Like let's say you have this just a big old pipe and there's just a wind blowing through and it happens to strike it at the right angle. Okay. Might set up some standing waves. Here's do you guys notice the roll? Guys, look at the roll here. Right. By the way, what I'm telling you right now, AP is not going to ask. Right? But is it high or low pressure points on the end? What do you think? This is gonna be low pressure. Low. Right. Now I'm representing a longitudinal wave with a standing, with a transverse, but it's not really a transverse. It's actually longitudinal, isn't it? Okay. Maybe this is a better picture. Okay. You guys, what about right above the water level? Is that a high or low pressure point? That's a high pressure point. Right. All the bunch together. Bunch together. Okay. What about the open end? It's probably a what? Yeah, low pressure point. Right. You guys kind of see a pattern here. Okay. Okay, that might be useful at some point. You can set up standing waves on strings.
Actually, I think I got a video of this here. Show you guys this right here in action.
Normally would.
Yeah. Okay. All right, so they got this oscillator. Okay, it's kind of bounce up and down. Okay. All right, there you go. Okay. And at some places, okay, so that's okay. Okay. At some places it'll set up a standing wave. Looks like okay, 11 hertz. And then okay, now he's pausing the video here, but ooh, 22 hertz. What do you guys think the next point is? Well, it'll set up a standing wave. Right. Okay. So now it's all muddled. Right. Okay. But it's increasing the frequency. Right. And then right there, 33 hertz. 33 hertz. Right. 44. Okay. So you guys get the idea, right? Okay. So these standing waves, these relationships, wavelength, length of the string. Any stringed instrument, okay, so guitar, piano, violin. Okay, usually the vibrating part of the string makes a sound is. Guys, how many proper wavelengths would this be?
And my string becomes 2/1.
That's half of a wavelength. Right? The full wavelength would be one full S shape. Right? So one full wavelength is up here. Right? So here, guys, this is right here. The full wavelength is actually double length of the string. Right? Little technical details, so I can fit into these formulas. Right? Here's your waveform. So speed equals wavelength and frequency. Remember the other day I did an example with you guys. If you're watching ocean waves come in to the beach, right, and you see the wavelength between from crest to crest on the ocean waves, right? You say, maybe the wave crests are striking the beach every 5 seconds. Right, just hits, right. So, guys, 5 seconds. What's the frequency? 1/5 hertz. Right, right. And you could you multiply this together and get the speed of those ocean waves coming in? You do that, right? Right. Okay. Well, okay. Now that can apply to any wave, like this here. Okay. Right, you guys ever tune a string instrument? Right, like turn the tuning peg, right, make it tighter or looser. Right, so you're changing this tension right here. Here's the linear mass density of the string. Right. Okay. So this. Right. Guys, remember this frequency corresponds to a musical note. So if you want the string to give you an A note, for example, right, its frequency is so many hertz, maybe 440 hertz could be. Right? There's some string tension that applies to that. Okay. So we got that. Okay. Got that. Did I show you guys this one?
No.
Right. All right. So what's the relationship among the musical notes in a scale? Actually, this one I did with you guys earlier today. Okay. So go from a root note to its octave. You can very simply double or half. You can go the other way, double or half the frequency value. Okay. 440 hertz, 880 hertz, or 440, 220. Right. Something like that. Right. Now, what about all the notes in the middle? I think this was Pythagoras back thousands of years ago. I think the story goes he was like walking along and heard people like hammering pots, and then he heard, oh, it sounds really good when some pots are hammered together at the same time. Right? What we call harmonization. It sounds like some notes would harmonize. So he got curious about this, and he started measuring the diameters of these pots and said, okay, there's these certain ratios that sound good together. Okay? Like maybe if two pots had the diameter of like 3:2 ratio, right? It's like 30 centimeters versus 20 centimeters, and pound put them together. Right? They sound nice together. Okay? Because they would harmonize. Right? Now, modern instruments use this scaling right here. Okay? Guys, how many unique piano notes are there before it cycles to the next octave, including all the black keys? They're 12. They're 12 different notes. Right? Right. You guys see it's 12 right here. So n can count like the number of keys up. Musicians might call that a half step. You guys got a calculator? Here, try this. Okay. Let's go up. Let's put 12 in. I should give you guys a picture too. Let's see. Piano. Okay, images.
I'm not doing it.
Sorry, the internet's being really slow right now. Okay. But let's count up 12 keys. So take some root note. Let's call it 440 hertz. I've been using this data. Times 2 to the power of, right? And then put 12 up here, 12 over 12. Oh, guys, what is 12 over 12? 1. What's 2 to the power of 1? 2? And, okay, so you guys see we effectively double like that. Right. Double. All right. You know what? If I click on one of these, it's going to take forever to load, but here, you can kind of see right here, right? So if here's like here's a C, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 gets up to that B, and then 13 would be back to C. So there's like 12 different. Right. How about this? What if you wanted the fifth Can you count up 1, 2, 3, 4, 5, 6, 7? It's like 7 notes up. Let's go 7 notes up and see what happens. 7 notes. Okay. Okay. So let's put a 7 right here. Okay. Actually, just do this. Let's ignore the original frequency. Let's just do this part right here. So do 2 to the power of. Everybody type that 2 to the power of, and then parentheses do 7 over 12. Right. We're gonna see. Right. Because that should be the perfect fit. Right. And what does that say right there? 1.498. Right. Ooh, guys, what is the ratio of 3 to 2? 1.5. Yeah, 1.5. Right. That's almost identical, isn't it? Almost identical. Right. Now it's off a tiny bit because those these are actually different systems. So here's like the Pythagorean tuning, and here's equal temperament. It's actually slightly different systems. So if you go back hundreds of years ago, instruments they were different tuning systems they used. So if you were a composer, if you compose something in the key of A versus the key of G, or C sharp, or whatever, right? It would actually sound different because when you change keys, every key was like had different kind of like flaws to it or get different characters. Modern instruments typically use this equal temperament, so you can switch keys and all sound sort of the same. All right, and I do have here. You guys ever stand by the sidewalk and a car goes by? And you hear a pitch shift. Okay, I do want to do this with you guys someday, but I do have to do an FRQ, so this will take a while to explain. Got sound on this. Okay. Anyway, let's hit this FRQ right here. You guys got an FRQ on your desks. All right, so good else, good new stuff. Good here. All right, FRQ time.
Your words and none of them.
Switch this.